Section 4.6, page 2. It's stuck right in the middle. It's kind of hard to see. Okay, example 1 says to use Newton's method to approximate the root of x squared equals 9 on the interval of 0 to 4, correct to 2 decimal places. Now, technically, we know the answer is 3, right? When x is 3, we're going to have 9 equals 9, which is a true statement, and we can consider it a root, which we're going to see in a moment, but we're going to look through the process anyways. So we aren't given an x1 to start with. Usually your best bet is to pick a value that's somewhere in the range that's given. And the midpoint's always a great starting point, but you could have picked, 1, 3, 4, 3.999. Now, the reason I say we're looking for a root is we want to create an equation that we can set equal to 0. So if I took that x squared equals 9, and I subtracted the 9 over, we'd have x squared minus 9 equals 0, where we know that this factors into x plus 3, x minus 3, giving us negative 3 and positive 3 for roots. But if we're only looking between 0 and 4, 3 is the solution. But let's go through the process. Newton's method says an output, a root, can be found by the previous value plugged into the function divided by the derivative of the function subtracted from that previous value. So in our case, our function is x squared minus 9. So we're going to put the previous x to the n in x squared minus 9. The derivative is 2x, so we're going to have 2 times that. And so here's the equation for this particular problem's Newton's method. We said we're going to start with x1 is 2. That means we have to find the next one. So where x to the 1 is, we put a 2 in all of these locations. So I get out my calculator, I type all this in, and I should get something not that far away from my previous value. 3.25 is not that far away, relatively speaking. If I got 32.5, I would be worried that I had some sort of order of operations issue on my calculator, and maybe I'd have to get a single value for the numerator, a single value for the denominator, divide those, and then do 2 minus this piece. So now, where this 3.25 is, I'm going to change these. So I'm maybe going to pull up this line on my calculator and back arrow and type over this and maybe hit my insert button to get 3.25, 3.25, 3.25, as you can see here. And I get 3.0096. Again, not that far off from where I was. Because we're supposed to be correct to 2 decimal places, I'm coming 2 decimal places over and rounding to get 301. So now, everywhere that x was, I'm putting 301. This is where it's much nicer. I'm going to back arrow and just do 0, 1, 0, 1, 0, 1, and I get 3,000. So when I round, I get 3 even. So again, I'm going to back arrow and just change these to zeros or delete them off, and I get 3 again. So I just found that x3 was 301. x4, well, actually, I guess we can look at it this way, was 3. And we just found that x5 is 3. So x4 and x5 are the same. So we're now correct to 2 decimal places. And our answer is 3, or you could say 3.00. Now, what if you have a slight twist on that same problem? Let's look at example 2. We're still asked to use Newton's method, and we're approximating roots of what we see as an equation, this time to 5 decimal places. Now, we're not given a range, and we could start with anything, but if you're not given a range, best thing to do is solve each of the equations or graph them and find their intercept. So like in this particular case, I know e to the x looks like this. I know that I may have seen this as negative 2x plus 5, so a y-intercept of 5 with a slope of down 2 over 1. They intercept somewhere in between 1 and 2. I mean, it might even be 1.5. But for ease, I chose to let x1 just be 1. You could use 1.5 thinking you'll get to your solution quicker. So we still need to set the equation equal to 0 though, because Newton's method requires a function, and what we have is an equation, not a function. So I'm going to add the opposite of the 2x to the other side to get a positive 2x. I'm going to subtract the 5 to the other side to get a minus 5. So I have my function, which is e to the x times 2x minus 5. And then I need the derivative. The derivative of e to the x is e to the x. The derivative of 2x is just 2, and, well, minus 5 is 0. So I'm going to take this derivative in the denominator, where the variable just becomes the previous value, and then Newton says to have that previous value minus this ratio. So we're letting x1 be 1. So in all of these spots, I needed to put a 1 so that I could find x2. I'm going to enter this into my calculator. I get a long number, but because we're going for 5 decimal places, 1, 2, 3, 4, okay, 5, I decide that that does round up to a 1, so I can then use that as my new value. 1 and 1.105, etc., not that far off. So in all of those spots where I had the orange 1, I now have my light blue 1.05, etc. number. My calculator gives me, oh good, they both start with a 1, and then a 0, and then a 5, oh, a 9 and 8, and even though this would round to 9, that's not where I'm rounding. So with rounding and this bumping to a 10, I end up with 70. Okay, so even though these numbers look close, they're not identical, so I keep going. Plugging it into all of these spots, where again, I only had to back up a few spots to enter a few different numbers, and now I've got this other number. When I round to the 5th place, I end up getting the exact same answer I just had, so I get to stop. It felt like going 5 decimal places for accuracy was going to take me a lot longer than x4 to find my solution, but I didn't. And remember, we're doing this to find a root to the problem. So if I took my original function and I plugged in the root, I should be getting 0. Now, I didn't get 0, but I got something pretty close. So if I wanted more than 5 degrees accuracy, I could get something even closer to 0.